right. Welcome, everybody. Welcome from my kitchen on this wonderful wintry spring day. Want to thank everybody for taking the time to attend, and as always, want to thank Kristen and Matt and the Monterey Bay Regional Climate Action Compact for hosting this. The webinar today is Passive House 101, an introduction to Passive House. And as similar to a lot of the stuff that we're doing with the Climate Action Compact right now, it's in the service of bringing awareness about very sustainable and energy efficient building practices to the Monterey Bay area, and working towards our goal of making much more energy efficient building practices mainstream in our area. So today, we're lucky to have Xavier with us. He and I are both members of the Passive House California Board of Directors. Xavier has been working in Southern California area for a long time and nationally to help bring awareness about these practices that we're hoping to get out into the public awareness. And Xavier has one of the first certified passive houses in Southern California, and has presented this material several times down there to jurisdictions and various groups in Southern California. And so, again, very lucky to have Xavier with us today. Thanks so much. And here he is.
Good morning. It's a pleasure to be here today. And don't adjust your sound system. That's a French accent that you're hearing. So that's me. And let me share my screen, and here we are. So, as Rob was saying, I'm a certified passive house consultant, and I'm the owner builder of the Purita Passive House, which was the first completed passive house in Southern California. And this is where I'm talking to you from today. And also I'm a board member of Passive House California, which takes a lot of my time and Jeanette, and hopefully you can join us. Passive House California is an affiliate of the North American Passive House Network, which regroups all the Passive House associations all across North America. We are promoting the Passive House standard, and we are all members of the International Passive House Association, IFA. Why am I here? That's my dream house that I built in France, or at least I thought it was. And a few years after completing that house, after fighting to get the building permit for a long time, I discovered the Passive House standard. And that was very frustrating to see how much I screwed up and how much I could have done way better. And so that's what actually started me with that journey. And the frustration has a lot to do with being more and more aware about climate change, about the impact that the human activity was having on the climate, and especially knowing that the building industry is responsible for a big chunk of the world's CO2 emissions. And so when I discovered the Passive House standards, it made a lot of sense to me. And but what is the Passive House standards? It's architects and builders have been working to make building more comfortable and more efficient for many years. You have that ancient Chinese building, with a ventilated roof that you have here. Maybe you can see my mouse. then that's a vegetation roof, in Denmark to increase insulation. And actually, the first passive house building was actually that boat, which was the Fram ship, and it was a polar expedition boat, and the captain, on his diary was writing, we're very comfortable. I'm even thinking about removing the wood burning stove because we never use it. And the boat had the triple pane windows and like a 1 foot of cork insulation. And so that's an interesting one. And so many other experimentations were done, with passive solar, with super insulation buildings, but all that was mostly done, was the rule of thumb and not very many physics studies behind it. And so you have two guys in the late 1980s who started to look at what was being done, and they actually discovered that more insulation did not mean necessarily more efficient buildings, and they started looking into it. And so they did many studies, and they actually built the first passive house in 1990 in Darmstadt, Germany, and that's the building. Today, the passive house standard is the leading low energy building standards with almost 100,000 buildings all around the world in every climate zone. And it's not only for single family houses, it's also for larger buildings. And you have actually here the Cornell Tech Tower, which is in New York, which is a 26-story building. And so all those experiments in science are led by the Passive House Institute. And we developed the Passive House Standard, which I'm going to tell you about. Basically, one of the first discovery, which was done by the Dr. Feist and the Dr. Bow, which were the two scientists who started the Passive House Standards research, is that actually comforts drive performance. And because they were not actually looking so much for performance building at the beginning, they were looking for comfortable building. And actually, the Passive House Standard is quite simple. It's very similar to your thermals versus your regular Starbucks coffee cup. And it's actually based on 5 principles, which we're going to detail through that presentation. But the primary features are very high efficiency, excellent comfort, and great indoor air quality and superior health, which brings energy affordability, resiliency, grid stability, and very low emissions, and all that will support renewable energy. The goal with that is that today the Passive House Standards allows to reduce the heating and cooling consumption by up to 90%, and the energy consumption by up to 75%. The way you have to look at it is that, like in a car, when you turn off the air conditioning, as soon as it stops, it gets hot again. The goal of the passive house building is actually to keep the indoor air temperature the way it is because of the building envelope. And so in that case, you need way less heating and cooling to make the building comfortable. And the Passive House Standard for the first 10 years, which was a lot of experiments and was not really picking up. But then the EU in 2000 commissioned a study to see how buildings were performing. And that study was done over 250 units. And what was really interesting is that after that study demonstrated that the Passive House Standard, it was only in average a 5% difference between the calculated numbers and the operating numbers. And that's, for legislators in general, the main goal is to actually that the rules and the building standards that you make the matches, the actual operation. And that was the first time that actually the numbers were demonstrating that they were working on the field. And that was one of the every time. And that was one of the big step forward for the passive house standard. As I was saying earlier, it's not, the passive house standards is not only for single family houses. It's also for very complex building. That's the bottom left building. Actually, it's an hospital in Frankfurt. We just passed the blower door test, the air tightness test, last week actually. That one is an office building in China. That one is the Belgian embassy in Kinshasa, Congo. So very different climates, very different type of building. And that one is the Cornell Tech building in New York, which is a 26-story building. So it's for every type of building. And also for retrofits, it's not only for new buildings. You can apply the passive house standard to existing buildings. And why the passive house standard is so important and the building is so important to fight climate change. Here's a graph, showing the New York path to reduce their CO2 emission by 80% by 2050, and you can see that big chunk here, that big red square is actually the building adopting the passive house standards, and that part reduces, helps to make 50% of the goals to reduce New York CO2 emissions. Vancouver also is adopting the passive house standards as part of their climate change fight, and the EU also is adopting it all across Europe through a standard which is called nearly zero energy buildings. So it is coming forward, and it is the 21st century building standard. Of course, people will mention the cost. That one was a study which was done in Pennsylvania in 2019. And the black dots here are conventional buildings, and the blue dots are passive house buildings. And out of 268 buildings, you can see that the average cost of construction for passive house building was actually less than conventional buildings. The thing is that when you design and when you build a building, you make so many decisions which will have a bigger impact than going for a very energy efficient building to none. That's if you start using the passive house standard and that you decide from the beginning, from the first line of the building that you're drawing, that you go for the passive house building, it won't cost you more. But the thing is that you have to decide that right from the beginning. It's not like a coat of green paint that you come applying on an existing design, or it makes it way more difficult, especially for the cost aspect. The goal, it's very simple. And it's 3 steps. The first one is that you focus on the passive house elements, which are the building orientation, the massing, how much thermal mass that you have in your building, the insulation, the air tightness, the windows and doors, and the passive heat gains. Passive heat gains are the people heat and the cooking and all the heat that you get for free. And then you have to meet those goals in terms of energy performance. So doesn't give you much. Just to give you an idea, the primary energy of 38 kBTU, it's basically 3 times less than any existing building in California. And just to give you an idea about the 3.17 BTU per hour per square foot, it's like for 1,000 square foot house, in every climate, you need a blow dryer to keep it warm all year round. So that's really nothing, and it connects to what I was telling you about the car, how it's not insulated and that you need constant heat or cooling to keep it warm and cool. That's the opposite with a passive house building. You keep it at you bring it to a certain temperature, and that it will need very little energy to stay at that temperature all year round. The main tool, the first thing that we use to design a passive house building is called the PHPP. It's the Passive House Planning Package, which is actually the tool which is going to help you control that you're reaching the numbers that I was mentioning about. So you're going to enter all your building data, because the devil is in the details. So it's a very simple but very detailed tool, which is Excel based, where you're going to enter all the information about the building, and which is going to tell you at the end if your design is going to pass or not going to pass. And so you change that until you meet the requirements, and then you can start your construction. What's very interesting about the tool is that, as the CFIUS study I was telling you about was showing it, is that it will allow you to match the operating numbers with the calculated numbers, and that's the one of the biggest assets of the passive house standard. The way before we go into the details and how do you make a passive house buildings, it's just you have those tools which we're using to make the standard work. The first one, which is really important, is the certified trainings that we have. Is that one is for consultants and designer, is for architects and engineers, and you have a training also for contractors. So how to implement what's being designed. You have the PHPP, which is the tool I was telling you about, the energy modeling tool. You also have a database of certified components, which actually guarantee you that the performance which are indicated by the manufacturers are the actual performances. You have the Passipedia, which is basically the Wikipedia of the passive house, because one major thing about the passive house standard is that you have a community of more than 10,000 people all around the globe, and sharing information, experimenting, trying new solutions, and all the validated solutions are available in Passipedia. And also that makes it very valuable, is that each time you're looking for a solution, someone did find an answer, and that makes it very comfortable much more comfortable to do a passive house building. And I'll tell you more later about my own experience. Of course, you have the certification process, which I'm going to tell you a little bit more about, and the Passive House Institute, where you have 60 building scientists, certifying buildings, improving the standards, and so on. So that's what makes, the passive house standard work. Regarding certification, the certification process is fairly simple. Everything is done actually remotely. You don't need to have any on-site inspection by the certifier. The only on-site inspection which is required is actually a blower door test, and we'll talk a little bit more later about that. But a fairly easy and cheap certification process. And all those are all the people who are certifying building across the US. Regarding the certification, one more thing is until 2015, it was only one passive house certification class, which was the classic one, which was certifying the building envelope and the building performance. Realizing that renewable energy was a big part of our future, the Passive House Institute introduced two new building classes. One is the Passive House Plus, which I would compare to net zero buildings, and the Passive House Premium, which is I would compare to carbon neutral buildings in terms of operation. The reason why it's very important to take in consideration the renewable energy and why energy efficiency is actually comes before the renewable energy. Is that if you look, at what a building is going to use, is that a decent part, of the energy that the building uses is directly produced by renewable energies, which are produced right away. It doesn't need any storage, and goes directly from your solar panels or your wind turbine directly to the house. The thing is that you actually have a lot of energy which needs to be stored, either a short-term storage or long-term storage. In the summer, you will produce more solar panel energy from the solar panels. That's what you will need, and that energy will need to be stored and to be delivered a few months later. The problem with energy storage is that the short-term storage, that the Tesla batteries, it's okay. You have a 80% efficiency, and that's acceptable. The main issue is that the long-term storage today, the solution that we have, they only have a 30% efficiency, which means you need to produce actually 2 to 3 times more renewable energy here. That's what is going to be used at the house. So that's why actually the energy efficiency of buildings or whatever equipment using electricity is very important. Is that ratio, which the Passive House standard called the primary energy renewable factor, which is that ratio between the final energy demand and the renewable energy supply. So that what's very important to understand is that when we talk about net zero, it's just a concept, because in the reality, you actually need to produce 2 to 3 times more renewable energy compared to what you will need at the end. Also, as I was mentioning, the Passive House standard is not only for new buildings, and they developed, what's called the NFIT, which is the Passive House standard for building retrofit. And I won't go into details today, but it's very interesting step-by-step renovation process, where actually you defined a roadmap for your building, for every existing building. So each time you do some work on that building, you know that it is according to that roadmap. And you know that when you're installing and you're replacing the windows when they need to be replaced, you know that you're putting the right type of windows, which are going to take you to the efficiency level, which is required when your renovation, which may take 5 to 10 years, whatever, to get there. You know what you're doing, and you're not shooting in the dark. So how do we make Passive House buildings? It's 5 key principles, which are quite simple. And if you remember something today, that needs to be it. It's especially if you're in the building industry. The first one is, of course, the insulation. And when we talk about insulation, we're talking about continuous insulation, roof, wall, floor, including if you have a slab. Okay, so it's like, when you go skiing, you put a big jacket, but you don't ski in shorts. Okay, same thing here. Okay, your building envelopes need to be all around your building. Number 2 is thermal bridges. Basically, a thermal bridge, it's a hole in that insulation. It could be, a slab going from inside the building to outside. It could be a beam. All that is a thermal bridge. Number 3 is high performance windows and doors. Of course, they are the weakest point of your building envelope. And so it's very important to minimize that weakest point. Airtightness is that to make your building airtight. We go see that in details. And the last one is high efficiency ventilation and continuous ventilation. So we go through each one. So first one is the continuous ventilation. Of course, you won't have the same insulation level in California or in Canada, so of course it's climate specific, and it will depend on the location of your building. You have to look at it, like the rating for sleeping bags, for example. If you go camping in the desert in the summer, or in the mountains, you won't need the same type of sleeping bag. Same thing here. What's really important is that you define your building envelope, and that's what you insulate. Okay, you don't need to insulate your garage. Okay, you insulate the building envelope. So first thing is that you define what is your building envelope, and that's where you install the insulation. In terms of insulation, it's when you look at Title 24, for example, it specifies a type of insulation. Like you don't have any, does not take in consideration if you have any framing or whatsoever, or if you have different components. Here, when you actually look at a regular building, you have several layers with different R values for each one of them. And actually it gets a little bit more complicated than that, because you actually have the framing. So the insulation will be the light gray part. But you have the siding, you have the stucco on the stucco, you have the drywall on the inside, and the framing. And of course, if you put a lot of framing or if you put little framing, the insulation value of your wall won't be the same. So that's all this information that you actually enter in the PHPP. And so you are going to enter each layer of insulation. You're going to enter the information about the framing that you have, and it's going to give you an actual effective R value, because the R value of your wall is actually different than the R value of your insulation. And that's one of it's an example here, but to see how the PHPP works is that you enter the exact design information about your building, which will give you, that's why it will give you the exact results. The number two is the thermal bridges. The reason why to avoid thermal bridges is that the first one is a health issue, is that's where you have condensation and moisture and eventually building damage, the thermal discomfort, and of course the energy losses. And so and it's something that barely any building designer calculates, but in some climates and some type of construction, especially if you build with concrete or if you build with metal, the thermal bridges can go up to 20% of your building loads. And so you actually will take that in consideration. Basically, where it happens most of the time, it's the corners, the connection between the floor and the wall, the connection between the roof and the wall. And so you're also going to take that into consideration, if you have any, into your PHPP calculation. Basically, thermal bridges, they happen everywhere you have a connection. When you have pillars where you have the connection with the roof. And just to give you an example here, if you look at a parapet here, that's, how it is done. Normally, you have the insulation, unfortunately. You have the insulation on the outside, the insulation on the roof, but here you don't have any insulation with the parapet. And you can see that you have a big thermal bridge of 0.25. If you look what another solution would be, which would be way better and which allows you to reduce your thermal bridging by up to 10 times, is actually insulating all around your parapet, but you're increasing the surface. Here, the best solution and the most cost-effective one too, especially, which is possible for new construction, is actually you have a thermal bridge break here that you don't really see. It's a darker gray here. So, which means you have your continuous insulation here. And you are going to reduce your thermal bridge between that version and that version by 25. Just an example of what needs to be done in order to reach high efficiency. And of course, if you're using wood, it's not as critical, but still it has a big impact on your performance and also on your building structure. Number three, the windows. Of course, it's climate dependent. In most cold climates, passive house will require triple pane windows. In my case, or in Southern California, we're often good enough with double pane windows, but it has to be high efficiency double pane windows. And there are several reasons for that. The first one, as I said, the passive house standard is not only about energy efficiency, it's also about the building comfort. And one of the comfort criteria is actually that you have less than 8 degrees difference between the wall and the surface temperature and the ambient temperature. And because above those 8 degrees difference between the surface of the wall or the glass, that's what creates discomfort. So that's one of the first reasons why you want high efficiency windows. And what makes high efficiency windows? That's a section here, is that actually you have the glass is of course a main part of the window efficiency, but also the frame. Is it thermal? Do you have any thermal break? In the frame, is it insulated? You also have the spacer. Lost my mouse. Here it is. You have the spacer here between the different layers of glass, which is very important. So basically, when you see, aluminum spacer between windows, walk away from it. It's because aluminum is a really bad thermal bridge. And so you know that the windows will have a very bad performance. And the last one, as you can tell, is that you have 1, 2, 3 layers of gaskets, because of course the windows need to be airtight. So that's a typical section here of a triple pane passive house windows. The high efficiency glass, high efficiency spacers, thermally broken insulated frame, and airtight. The other thing which is really important in California or in hot climates, it's actually the shading. And one thing is that internal shading doesn't work. Okay, the heat is already inside the building, so the only thing which will help you to fight your cooling load is external shading. External shading can be, awnings like here, or outdoor blinds. The thing that you have to know is that awnings don't really work for west exposed windows, because the sun is too low to allow the awnings to do some shading. Shadings work really well for south-facing windows, because when the sun is high in the summer, it shades the windows, and when you need the solar heat gains during the winter, it will go right at your window. So shading is a really important part. And so all the shading, especially here in our climate. So all those information, including, the outdoor elements like trees, hills, or whatsoever, all those information will be entered in the PHPP in order to give you the exact figure about the cooling load and the comfort, especially related to the summer months. Number 4 is the air tightness. And it's actually in California, it was one of the study we did. It's actually the biggest gain compared to existing buildings and the actual code. It's the number that you have to meet is that you do a blower door test, okay? And so you measure the airflow which you need to bring in order to keep your building under pressure, and that gives you how leaky is your building. The reason to have airtight building, it's to prevent condensation, to prevent the drafts, to have proper indoor air quality. The sound insulation is great. By the way, my neighbor is using his blower. I hope it's not disturbing you too much, because we can still hear it a little bit. But there are a lot of reasons to build airtight. And the main one the main ones in California as the indoor air quality, the sound, and the drafts and the waste of energy that you are adding. And so that's actually the one of the biggest, or the only, I would say, or the main design challenge is that to design your air tightness strategy, because actually it's more a design challenge than a construction challenge. If you architects, design the proper construction details, it will be easy to implement. And so what you have to give to the construction crew is how actually that detail is going to work and how the continuous air tightness is going to be maintained. But while that is done, it's fairly easy. You have a lot of materials and equipment to make it work. It just needs to be designed properly. And at the end of it, I mean, not at the end of it, actually, you use a blower door in order to test that. You have to do both tests, negative pressure and positive pressure. That's how you control the air tightness of a building. And there is something that you cannot make an energy efficient building without doing an air tightening test. That's not possible. And just to give you an idea, that's my house, and if we calculate the size of the hole of that passive house, it's a 5-inch hole. Okay, so if you combine all the holes, it's like having a 5-inch hole. And we are it's a retrofit, so we were allowed to 1.0 ACH50, which is the metric that we use. New construction in California, several surveys were done. The ACH50 is about 6, so it's about 6 times bigger than my house, or even 10 times higher than new construction. It means for every new building, you have a 16-inch hole, 24/7, all year round in your house. How can you expect keeping a building comfortable with this window open all year round? So that's something that you have to keep in mind, is that air tightness is really, really important, even if so far the code doesn't believe so, but we're working on that. The last principle is the continuous ventilation. It's something which is really important. It's not possible to have proper indoor air quality without any mechanical ventilation, unless you're outside or your windows are open 24/7. But if your windows are open 24/7, you're not comfortable. So in a comfortable building, in order to be able to have a proper indoor air quality, you need mechanical ventilation. And the thing is that in a passive house building, why you need the airtight envelope is that you know the exact amount of pressure that you need to bring, because you know that no pressure is going to come from the building leakage. And so if you actually compare a regular house with a passive house building, that's the CO2 level. That's the easiest way to control the indoor quality of a building, is that you see a regular house, when you actually open the windows, like here, the CO2 concentration in the building will drop, but as soon as you reopen the windows, it goes right back up. And so the only way in order to avoid that, going up and down, or going down only when people are leaving the house, is actually to have a continuous ventilation, which is the red line that you have here. What's important to understand is that if you reach above 1,000 ppm or 12,000 ppm, that's when you have inadequate ventilation, and it's a lack of concentration. That's when you start having headaches, you have general drowsiness, and basically in general, it reduces your intellectual abilities. And something that I discovered recently, which was actually, and I digged into it, is that if you actually look at the different, global warming scenarios, the red one is the one that if we continue doing business as usual, this is where we are now. And actually, today the world's CO2 concentration outside is about 400 ppm. If we keep going that way, before the end of the century, the CO2 level in the atmosphere is actually going to be above 1,000 ppm. So which means we're going to be, it's going to be more than what's required now inside. Okay. So, it's a bit scary. So if you have some time, actually, I recommend a movie, and that's also another reason to keep the CO2 level below, because not only, we're going to be doomed with the global warming, but we're going to get dumber. So, interesting movie. Just going back to the ventilation, the way it works is that you actually bring fresh air in all the living spaces, like a bedroom, living room, and so on. And you are extracting air in all the dirty rooms, the bathroom, the kitchen, and you're using always as transfer zones. So you bring fresh air in all those rooms, and then it transfers to the dirty rooms and the extracting zones. And so you have actually your airflow, which is renewed in your building. Basically, every 3 times a day, the entire volume of your house is going to be renewed. That's what we guarantee great indoor air quality. And the way in order to minimize the heating and cooling load of the fresh air, continuous fresh air, is that most of the time we use what we call an HRV, heat recovery ventilation unit, where the fresh air the fresh air coming in is going to go through that heat exchanger and going to get the heat in the winter, get the heat from the air that you're extracting. And so which means the fresh air which is coming inside the house is going to be way warmer than what the outdoor temperature is. Just to give you an idea, when the outdoor temperature is about 0 degrees, and so you're extracting air at, let's say, 65, 66 degrees, the fresh air here will come inside the house at more than 50 degrees. So it's a very efficient and very inexpensive way to warm up your fresh air. And that's in 90% of the cases, that's a piece of equipment which is required in a passive as well. So all that was the general concepts. And so I just, sorry, go back here a little bit. I missed that slide. I just would like to refresh everyone's memory. So I've got the slide. So I'm just going back here. So 5 key principles. Continuous insulation, depending on the climate where you are. And that the PHPP, which allows you to see how much insulation that you need. Minimizing thermal bridges. So basically minimizing any holes in that insulation envelope. High efficiency windows and doors and shading, especially in hot climates. Air tightness and continuous ventilation. And that's what makes a building energy efficient. So let's look at what it means in California and how does it work in California. Sorry for that. Several studies were done. Passive House California did that study in 2013 and was comparing for a single family house the energy saving that you would have, between a passive house building and a regular building. And actually, the study demonstrated that depending on the climate, we have 16 climate zones in California. it goes to 39 to 83 reduction of the heating and cooling, depending on the climate. So still a lot of big gains. And last year, the California Energy Commission and the case study did a case study about passive house building for multifamily houses, and same thing, and the numbers were even higher. So the passive house standard, it works very well in California, and it's actually easier to achieve than in many other climates. That's my house, and I just would like to share with you some of the results that we obtained. And it was an energy efficient renovation, and so that was the house is located in LA, Los Angeles, in climate zone 9, and so Title 24 required R13 insulation, which is actually R11 if you take in consideration the wood. We basically added one layer of insulation in order to meet the passive house requirements. For the floor, Title 24 required R19 insulation. We used R21, so basically that's the same price, no increase there. And for the roof, the Title 24 were requiring R30, and we used R38, which gave a R34 actual R value for the roof. The windows also a little bit more efficient, and the biggest change is actually the ACH50, so the blower door test. We reached 0.9, which was okay because it's a retrofit. For retrofit, you have to go below. You have to be below 1.0. For new construction, is 0.6. When new construction in California, even if blower door tests are not done, but several surveys were done, it's actually 6. So that's the biggest difference compared to standard. That was the biggest difference compared to standard construction. And what's important one more time here is that, so 15 plus 13 equals 22. It means the actual R value of your walls is not just insulation, it's how well the framing was done. That's when we talk about advanced framing and all that stuff. It's in order to maximize the insulation and your actual R value for your wall. And in our case, going from those numbers to those numbers, in terms of heating demand, we were able to reduce our heating demand by 69% and our cooling demand by 57%. That's huge. And going back to the cost, comparing, the cost if we would have built, the house according to Title 24 and the price difference. The price difference between the two was a little bit more over $20,000, so plus 3.6% of the total cost. Knowing that project was done, we built the house 2015. We did the work in 2017. And I just moved from France, in 2015. So I was fresh off the boat. So I'm sure, more experienced contractors and designers can do way better than that. But just to give you an idea, it's what does it takes, and knowing that none of the crew that we had on the building were familiar with the passive house standard. And so we had the only rule that's something that I did is that no one would touch a tool on the job site until they had a 15-minute presentation about what we're trying to achieve and what it was important to do that. That was the key aspect here. And so just giving you an idea of what it means, in terms of energy efficiency. I did a graph here. We measure, the EUI is basically, the miles per gallon for buildings, or the gallon per miles, I should say, because they actually lower the number, better it is. And so the Los Angeles average building, they have an EUI of about 40 kBTU per square foot. Okay. The passive house standard requires, the EUI to be about 15 kBTU. So actually, more than 3 times less than conventional building. When you look at Title 24, it's a decent building code. The thing is that it's missing so much thing that you don't know where you're shooting. And when I was talking about the accuracy, about the PHPP, that it goes, the devil is in the details, is that that's what it shows with Title 24. You can do great Title 24 buildings if your building is airtight. I mean, all the things which are not included and which you can do better. That's what's required, and it's actually easy to do better. And you can see some passive house buildings with an EUI around 20, and that's pretty good. But you can also have Title 24 building with an EUI which is 35 or higher, which is actually almost as bad as existing building. So that's one of the issues. And also another thing is that when you look at the ASHRAE standards, still today requiring an EUI around 28, which is 2 times more what the passive standard is requiring. We know, the industry needs time, and I mean, that's what Vancouver is doing. Vancouver is giving time to the builders, and they say, okay, the passive house standard is going to be required in 3-4 years. Okay, so you have time to get up to speed. But making people believe that the 28 kBTU per square foot EUI is decent is for me, it's criminal. I mean, it's just, it does not make sense. Especially when you look, how many solar panels. Today, our house is net zero with 12 solar panels. We produce the same quantity or a little bit more energy. That's what we're going to use on a 12 months period with 12 solar panels. And so if you do a passive house building right at the limit, you need 14. But if if you equip your same size 2,000 square foot house with solar panels with an average energy efficiency, you will need 38 solar panels. If you build to the ASHRAE standard, you will need 27 panels. If you build to the Title 24, you will need between 19 to 34 solar panels. And so remember what I told you earlier. In order to meet carbon neutrality and in order to have all renewable energy, we actually need to produce 2 to 3 times more energy. That's what's required at the building level. So all those numbers, you actually need to multiply them by 2 or 3. And so that's actually, and that's the huge part. And so when that's a slide from the project solutions, the study which was done all over, the US and even all around the world, how a country or a region can reach all renewable energy. And it gives you that breakdown. The thing that we forget is that here, we need to reduce the energy demand. The all renewable energy future, which is required in order to lower CO2 emissions, requires a huge reduction of the energy demand. The average reduction that we're talking about is minus 50% of our energy consumption. So there is no renewable energy future possible without a huge reduction of the energy consumption. And today we are far, far away from that, even in California. And so that's why the passive house standard is so important for me, is that actually in the building industry, we have the solution in order to reduce drastically that energy consumption that we know in some other domain and other sectors is going to be way harder to reach those numbers. In the building industry, we know how to get there. We need even to go out lower than that. So we're coming to an end. I hope I'm doing okay with time. The training is the most important part. Of course, with what's going on, the trainings are being a bit changed. But we are working for the designer and consultant training on remote courses, and I hope that we're going to be able to post those classes quite soon. And there is another certification for contractors, which we will post some dates on our website. All the trainings available in the US, you can find them on NAPHM website under the training tab. Please join us. We need you. We need your support. We need your feedback. PassiveHouse.cal.org. Please join us. We need your membership. You got an amazing community. You get access to a lot of Passive House materials. Go take a look. Now there's a great conference where it's a great opportunity to actually meet people from the Passive House community. For me, it's one of the biggest value of the Passive House standard is its community. You have amazing people all around the world ready to help, all around the US. Those guys will make 20-story Passive House buildings and more. That's where you meet them. That's where you listen to them. It's really great conferences, very inspiring. And now it's actually, you can save money and save carbon and register online at ephnconference.com. One last thing is that, of course, buildings are not the only thing, and we have everything in our day-to-day life. There are efforts that we need to make in order to reduce drastically our CO2 emissions. But in the building industry, is that the operating cost, today is about 80% of the CO2 emissions of typical buildings, and the rest, is the embodied energy, is all the CO2 emissions related to the building, to the construction materials that you use. Of course, when you start making high efficiency building, you reduce drastically that energy consumption. So, which means in terms of proportion, the CO2 emissions that related to the construction becomes way higher. And also another point is that those CO2 emissions, they are now. The operation, it's around this 50 years life cycle of the building. So please, if you considering, and as you should, make very energy efficient buildings, also take in consideration the materials that you're using. And for example, foam insulation, not okay. Okay, we're missing a point here if we're making high efficiency buildings with high embodied energy materials. That's, as we say in French, we need you. Nothing will change, without everyone getting on board and doing a little part of what needs and what should and what can be done. And so hopefully it was clear enough, and I motivated you today to go a little bit further and to dig a little bit deeper into that. Contact you have all the Passive House certified people in California. You have more and more available on Passive House California websites. You have a big community, so ask questions and starting now.
So if anybody has questions, they can write them in the chat. They can put them in the question and answer. If you put it in the chat right now, I can pose question to Xavier right now. You can also get in touch with us, Xavier and I, through Passive House California. You can get in touch with us through the Climate Action Compact. You can get in touch with me through my business, which is Karma Building and Design. You can write me there. But definitely, we want to be a resource for you. So Robert Frischmuth asks Xavier, how about house internal thermal storage? So I think he's probably talking about the thermal battery idea. Do you want to expand on that a little bit?
Are we talking about thermal mass or battery storage? I'm not sure.
I think he's talking about a passive house as a thermal battery.
Okay. Yeah, I mean, the best energy is the energy that you don't spend. So which means I don't have any graph to illustrate that. But the thing is that you, as I was explaining, I'm doing the analogy with the car. Here in the passive house, your blow dryer, in the wintertime is keeping it warm and it's kicking in, barely, we here, we've been home, my whole family for the last 3 weeks. The heat barely kicks in, and it's in the 40s at night, in LA, and so that's that's also one of the great benefits of the passive house construction, is that when everybody and when you have the peak of demand of electricity, when everybody comes in, and kicks in, the heater at night, or the air conditioning in the summer, your passive house has a steady temperature, and which allows the grid stability. Yes, it is. That's one of the big feature, and why utility companies should look more and more into the passive house standard.
Right. So on a macro level, one of the big issues in achieving carbon neutrality is what they call load shaping, which is the dirtiest energy that we have that we're using is the energy we're using at peak demand, which is in the evening when they have to the grid managers have to turn on dirty power plants to reach that extra peak demand. Also, solar energy is obviously available. The most of it is available at noon, right? And as the sun goes down, it goes away. For grid managers, one of the issues with moving to renewables is that renewables, generally speaking, are not as controllable as carbon-based energy sources. You can't turn on the wind when you want it to turn on. So, being able to use passive house or buildings that can detach from that diurnal cycle is one of the sort of reasons to consider it to help with the storage problem. At the end, Xavier also talked about embodied carbon. I just want to sort of give another plug for the NAPHN convention in June. One of the things that we're going to be doing this year is working on how to entrain embodied carbon software into the PHPP. That's something we're working on right now. And as a matter of fact, I'm actually designing a building that's going to be a passive house right now. And this is going to be, we're sort of shadowing the process with one of the tools for quantifying the embodied carbon in the project. So for the first time, we're going to be trying to work out how much embodied carbon is in the materials and being able to start to more clearly understand how to drive down that. So as I've been talking, we have another couple questions coming in. One is from Karen, and it says, do passive house standards preference decarbonization? And you want to take a crack at that, Xavier? Or I can.
Why don't you start?
So Karen, Xavier mentioned in the middle of his presentation when the passive house standard changed to have two extra levels, passive house plus and passive house premium. And at that time, they changed the standard to more fully align with the move towards renewable energy, with an eye towards augmenting passive house as a tool to align with decarbonization goals. So that, and this is like a lot of things when you get into the software, the explanation can get complicated, but they came up with a very detail-oriented matrix of considerations to figure out what the embodied carbon was on energy at any given location. In other words, when you do a passive house in a PHPP, you have to load in where the house is because it figures out the climate zone there and how much, what the demand is likely to be given the climate conditions. Also now has a metric for identifying what the carbon footprint of the energy you're getting in any given location. So they're doing these guys that came up with this, people in Europe in the 80s and 90s that originally originated this, the standard, and as they go along and continue to try and improve it, they are very cognizant of and doing a very detailed analysis of how to design that software to reach the goals. And yes, decarbonization is foremost in our mind with regard to why we're pursuing this. I hope that answers your question. I don't see any more questions right now. Go ahead.
There's one about the windows and the cold upstairs from Heidi. Should we address that, I think? Rob?
Yeah, I'm looking for it from Heidi.
It's, regarding the cold upstairs, the hot upstairs and cold downstairs, definitely. The thing is that by building that tight envelope, and you actually have a constant temperature all across the house. I remember, I don't know if Mike is here or not, but I did a tour of the house. It was 117 degrees outside the house, and we were actually in the attic, and the attic is part of the building envelope in my house, and you actually at the same temperature in the attic as what you have all around the house. So definitely, yes, the passive house standard helps the hot and the hot upstairs and the cold downstairs. Also, regarding the question regarding the windows, let me regulate people open windows.
I answered that one I answered that one directly.
Okay, right.
I think we're covered. I think we got everything we've come in answered. We're a little over time now, so probably, although you did great on time, if you were asking. So thanks again so much, Xavier, for taking the time to do this. I hope everybody got some useful information, but again, feel free to reach out to us if there's anything else you want to talk about. And please do try and support us if you want to become a member of Passive House, or you want in the local community to be part of our initiative here with the Climate Action Committee. Please reach out to them. And we're going to, my personal goal is to get 1,000 Passive House buildings built in the Monterey Bay Area by 2030. That's sort of one of my underpinnings of the initiative we're working on here. So again, thanks everybody so much for attending, and hopefully we will talk again soon.
Thanks, Joel. Thank you, Rob.
Yes,
thank you, Matt.
Guys.